The summit of Mount Everest is made of ancient seafloor. This video will transform how you see every mountain range on Earth. We are going on a geological detective hunt to uncover a planetary secret. The world's highest peaks, from the Himalayas to the Andes, hold direct evidence that they were once submerged beneath vanished oceans. You will learn to read the cryptic clues hidden in stone, the fossils and minerals that act as a time capsule from an age when oceans covered the continents. How can a seashell end up thousands of meters above sea level? What force is powerful enough to lift the bottom of the sea into the sky? By the end, you will possess a new lens to view the solid ground beneath us not as permanent, but as a page in an epic story of deep time and titanic collision. What does it mean for our understanding of the world to know that its most enduring landmarks are born from the sea? The story begins with a single, staggering number. 4.5 billion years. That is the age of our planet, a span so vast it defies everyday understanding. We measure our lives in decades, our civilizations in millennia, but geology operates on a different clock entirely. To make sense of a seashell on a mountaintop, we must first learn to think in what scientists call deep time. It is the grand, slow-motion theater where Earth's greatest dramas unfold. One powerful way to grasp this scale is to compress all 4.5 billion years into a single calendar year. On this cosmic timeline, Earth forms on January 1st. The first simple life appears in the oceans around late March. Dinosaurs rule the planet from mid-December until their sudden departure on December 26th. The entire saga of human civilization, from the first cities to this very moment, unfolds in the last frantic seconds before midnight on December 31st. In this year-long story, the colossal uplift that raised the Himalayas, pushing ancient seafloor towards the clouds, is not a sudden event. It is a process that begins in early December and continues for days. This is the essential perspective. The forces that shape continents are not swift or violent in human terms. They are patient and persistent, exerting a gentle, unyielding pressure over epochs. Geologists are the readers of this immense storybook. They do not have a time machine, but they have the next best thing, the rock record. Each layer of sandstone, each band of limestone, is a page inscribed by the environment that created it. A shale layer rich with tiny sea creatures tells of a quiet, deep ocean floor. A bed of coarse sandstone speaks of ancient river deltas or beaches. By reading these pages in sequence, from the deepest, oldest layers to the youngest at the surface, scientists can reconstruct entire lost worlds. This is why deep time is not just an abstract idea, it is the very foundation of the mystery. Without it, the notion that an ocean once sat where the Alps now stand seems like pure fantasy. But within the framework of these billions of years, it becomes not only possible but inevitable. The Earth's crust is not a solid, unbroken shell. It is a dynamic mosaic of tectonic plates, colossal slabs of rock that float on the planet's hotter, softer interior. They move at about the speed your fingernails grow, an inch or two per year. It seems insignificant, yet over 10 million years, that slow creep amounts to over 150 miles of movement. Over 100 million years, it reshapes the entire face of the planet. This is the slow dance that deep time allows, a waltz of continents that collides oceans and crumples seafloors into sky-piercing peaks. Accepting deep time is the key that unlocks the entire narrative. It transforms the impossible into a logical, evidence-driven detective story written in stone. A climber's hand brushes against cold stone on a windswept ridge high in the mountains, and their fingers trace the unmistakable spiral of a seashell. This is not a trinket dropped by a passing hiker. It is a fossil embedded in the very bedrock thousands of meters above any ocean. This discovery is the first and most visceral clue in our geological mystery, a paradox written in stone. How does a creature that lived in a warm, shallow sea come to rest on a roof of the world? The answer is not a freak event, it is a signature. These marine fossils, from delicate shells to the intricate skeletons of ancient creatures, are direct evidence of the environment in which the surrounding rock was born. They are time capsules preserving a moment when that spot on the globe was not a stark peak, but a sunlit seafloor. Take the summit pyramid of Mount Everest itself, a place synonymous with the ultimate terrestrial challenge. The rock there is a gray limestone, and within it, geologists have identified the fossilized remains of crinoids, animals that looked like feathery lilies rooted to the ocean bottom, and trilobites, hard-shelled arthropods that scuttled through ancient seas. These were not mountain dwellers. They could not have been carried up by a catastrophic flood or dropped by a bird. The physics and biology simply do not work. They lived, died, and were buried right where we find them. Their presence is a silent, steadfast testimony. The limestone that now forms the highest point on Earth was not always a mountain. It was once a layer of sediment accumulating at the bottom of a vast, ancient ocean, teeming with life. The fossil is the proof, and the altitude is the puzzle. This clue transforms our understanding of the landscape. Every fossil-laden layer in a mountain range acts like a page in a passport, stamped with the coordinates of its origin. A shale full of tiny, floating ammonites speaks of deep, open water. A sandstone with the imprints of wave ripples and burrowing clams tells of a sandy shoreline. By reading these pages, scientists can reconstruct not just the fact of an ocean, but its character, its depth, and even the climate of that lost world. The fossil is therefore more than a curiosity. It is a definitive environmental witness. It states without ambiguity that the forces which built these mountains did not create new rock from nothing. They took pre-existing chapters of Earth's history, entire ecosystems preserved in stone, and lifted them into the sky. The seashell on the ridge is not out of place at all. It is precisely where it should be, waiting for us to decipher its true story, a story that begins beneath the waves and ends in the thin air of the peaks. But fossils are not the only storytellers trapped in the stone. To truly grasp the scale of these vanished oceans, we must learn to read the language of the rock layers themselves. Picture the iconic walls of the Grand Canyon, a colossal library of Earth's history with each colorful band representing a different chapter, a different environment from the distant past. Now imagine that entire library, not carved into a desert plateau, but standing on its end, tilted and twisted, forming the very backbone of a mountain range. This is exactly what geologists find. The second, and perhaps even more compelling clue, is the presence of immense, uninterrupted sequences of sedimentary rock thousands of meters thick, perched at impossible altitudes. Sedimentary rocks are not born from fire or pressure deep within the earth. They are born from stillness and accumulation. They form grain by grain, layer by layer, in placid environments where sediment can settle out of water or wind and slowly harden into stone. Sandstone tells of ancient beaches or vast deserts, its rounded grains once tumbled by waves or winds. Shale, a fine, often flaky rock, speaks of quiet, deep water where the tiniest particles of mud could drift down and settle for millennia without disturbance. And then there is limestone, the star witness for our mystery ocean. Limestone is composed primarily of calcium carbonate, the same material that makes up seashells, coral reefs, and the skeletons of countless tiny marine organisms. It does not form in rushing rivers or on dry land. It almost exclusively forms in clear, warm, shallow seas, either from the direct accumulation of those organic remains or from chemical processes in seawater itself. Finding a single layer of limestone is a strong hint, but finding a vertical mile of it interwoven with shale and sandstone is a deafening declaration. This thick, orderly stack is an archive of time, proof of a prolonged, stable period where an ocean basin existed for millions upon millions of years, quietly collecting its muddy, sandy, and shelly pages. The profound contradiction is in their current location. These are delicate rocks formed in some of the planet's most tranquil settings, yet they now form jagged cliffs and sheer faces that defy gravity. They were created horizontally, layer upon flat layer like pages in a book, but in the mountains we see them folded, fractured, and thrust vertically towards the sky. This violent contradiction is the key. The rock layers themselves are not lying. They faithfully record their origins at the bottom of a sea. Their current, tortured state is the undeniable signature of a later, catastrophic force, a monumental geological upheaval that did not destroy the archive, but instead carefully preserved it, lifted it, and contorted it, placing the quiet seafloor onto the roof of the world. The story is written in the very architecture of the mountains, a testament written not in ink, but in the uplifted pages of ancient seabeds. The final and most definitive clue comes not from the quiet sediments of the seafloor, but from its fiery, volcanic heart. High in the Alps or the remote peaks of Oman, a geologist's hammer strikes a dark, dense rock. Its surface is not smooth or layered, but shaped into strange, bulbous mounds that fit together like a pile of stone pillows. This is pillow basalt, and its formation is a geological fingerprint. This rock only forms in one very specific environment, when red-hot lava erupts directly onto the deep ocean floor. The surrounding seawater is so cold and under such immense pressure that the lava cannot flow. It instantly chills and solidifies, squeezing out into these distinctive, rounded shapes. Finding pillow lava on a dry mountain ridge is not a suggestion. It is a statement of fact. It is the equivalent of discovering a perfectly preserved deep-sea submersible parked on an alpine meadow. The evidence is that direct and that undeniable. These pillow lavas are rarely alone. They are part of a larger, telltale sequence of rocks that geologists call an ophiolite. Think of an ophiolite as a complete, disassembled kit for building a piece of ocean floor, now lifted onto dry land. Beneath the pillow lavas, you often find a complex crystalline rock called gabbro, which represents the deeper magma chamber that fed those underwater eruptions. Interlayered with the pillows, you might find bands of a sharp, glassy rock called chert, composed of the silica skeletons of countless microscopic sea creatures that rained down onto the volcanic seafloor over eons. Together, this package of rocks, the gabbro, the pillow basalts, and the deep-sea sediments, forms a unique signature. It is the unmistakable calling card of oceanic crust itself, the very foundation of the ancient sea. This transforms our understanding completely. We are not just looking at sediments that settled in an ocean that once covered a continent. With an ophiolite, we are looking at actual, physical pieces of the ocean basin's own floor, its volcanic plumbing and all. These are colossal slabs of Earth's architecture, sometimes miles thick and hundreds of miles long, that have been surgically removed from their birthplace on the deep sea floor and transported intact onto the continents. They are displaced fragments of a world that no longer exists, silent monuments to oceans that have been entirely consumed by the planet's relentless tectonic engine. The presence of an ophiolite in a mountain range is the ultimate proof, the smoking gun in our detective story. It tells us that the mountains were not merely flooded by shallow seas, but that they are literally built from the stitched-together remains of entire oceanic worlds, raised in a monumental collision between continents. Buried within the gray limestone and folded sandstone, a more subtle messenger waits. It is not a fossil you can hold in your hand, but a grain of sand with a story to tell. Its name is glauconite, and it forms not in days or years, but over millions of years of perfect stillness. This mineral is a patient recorder, a chemical witness to a very specific and profound environment, the cold, dark quiet of the deep sea floor far from any shore. Imagine the deepest parts of our modern oceans, places where light never reaches, where the water is near freezing, and the only movement is the slow, gentle rain of microscopic particles from the world above. In that profound calm, under immense pressure and with just the right chemistry, glauconite slowly crystallizes. It forms within the tiny pores of other sediments, like a guest that moves in and never leaves, gradually turning a greenish hue. This is a crucial detail because glauconite cannot form on land, in warm, shallow seas, or in turbulent coastal waters. Its very existence is a locked chemical message that states unequivocally deep marine setting. So when a geologist takes a sample from a mountain rock, grinds it thin enough to see through with a microscope, and spots those distinctive green grains, the deduction is immediate and powerful. This rock, now part of a towering peak, was once part of that dark, tranquil abyss. The survival of this delicate mineral is itself a minor miracle. The process of mountain building involves unimaginable heat and pressure, forces that routinely erase such fragile signatures. Yet here it is, glauconite grains preserved like tiny time capsules that survived a planetary upheaval. For scientists, these grains are more than just clues, they are trusted coordinates. By mapping where glauconite is found, they can start to draw the outlines of those vanished oceans, charting the ancient seafloor that was destined to become the foundation of continents. It is a humbling thought that the color green in a mountain stone can whisper of a world of perpetual night and crushing depth, a world that vanished hundreds of millions of years ago, only to resurface in the thin, sunlit air of the summits. Sometimes the most important part of a story is not what is written, but what has been torn out. High in the mountains, a geologist's trained eye spots a line in the cliff face that is more than just a boundary between two layers of rock. It is a scar in time itself, a profound silence in the Earth's memoir known as an angular unconformity. Picture this, a lower section of rock, its layers once flat and orderly, now dramatically tilted on its side, like a stack of books shoved by a giant hand. These tilted layers have been planed off, worn flat by wind and water over countless millennia, and resting directly on top of this eroded, ancient surface is a new sequence of rock, its layers perfectly horizontal and undisturbed. This is not a simple transition, it is a confrontation. The lower, tilted rocks tell a story of dramatic upheaval, a chapter where the land was folded and fractured in the early throes of a mountain-building pulse. The flat, eroded surface atop them speaks of a long, quiet period of peace, where those newborn hills were slowly, patiently worn down to nothing, and the new, horizontal layers on top. They are often marine sediments, limestone or shale, whispering of a calm, shallow sea that returned to cover this worn-down landscape. That single line of contact, that unconformity, represents a gap in the record that can span tens of millions of years, an entire volume ripped from the planetary chronicle. It is a testament to cycles so vast they humble human history. The sequence is a powerful narrative. First, an ocean lays down sediments. Then, tectonic forces compress and tilt those seafloor layers, beginning the birth pangs of a mountain range. Erosion then takes over, grinding those first peaks back down to a flat, featureless plain. Finally, the land subsides or sea levels rise, and the ocean floods back in, laying down a new chapter of sediment on top of the old, eroded world. This is the cyclical heartbeat of the planet, written in stone. The unconformity does not just record time that passed, it records monumental events that were themselves erased by time. It is the geological equivalent of finding the foundation of an ancient, ruined city buried beneath the streets of a modern one, with only a layer of soil between them to mark the centuries of abandonment and forgetting. In the mountains, these gaps scream of tectonic drama, of landscapes that rose and fell long before the peaks we see today ever pierced the clouds. They force us to realize that the story of the sea covering the land is not a single event, but a recurring theme in Earth's deep history, a rhythm of submergence and emergence written in the very architecture of the highest places on Earth. The clues are undeniable, but they demand a mechanism of almost unimaginable power. To make sense of a seashell lifted miles into the sky, we need a force capable of moving continents and swallowing oceans whole. That force is plate tectonics, the grand unifying theory of geology that transforms our collection of clues into a coherent, breathtaking story. It reveals that the Earth's solid crust is not a single, unbroken shell, but a dynamic jigsaw puzzle of about a dozen major plates, each dozens of miles thick, all floating on a hotter, softer layer beneath. They drift at the speed your fingernails grow, a few inches per year, a motion so slow it feels like stillness. But over millions of years, that slow creep becomes a planetary rearrangement. This is the engine that drives the entire mystery, the reason why the quiet archives of the seafloor end up in the violent realm of the peaks. The story of the Himalayas provides the perfect script. For nearly 200 million years, the Indian subcontinent, a passenger on its own tectonic plate, journeyed northward across the ancient Tethys Ocean. Ahead of it lay the massive Eurasian plate. Between them was not empty space, but an entire ocean basin, its floor made of dense, heavy oceanic crust. As India closed in, that oceanic crust, the very floor of the Tethys, faced a fate dictated by gravity. It was forced downward, diving beneath the Eurasian continent in a process called subduction. Think of it as a colossal conveyor belt descending into the Earth's mantle, slowly but relentlessly consuming the ocean itself. For eons, the Tethys Ocean vanished into the planet's interior, its seafloor recycled into magma. But the ocean's story was not over. Its most enduring chapters were yet to be written. The sediments that had accumulated on that seafloor, the limestones and shales full of fossils, were too light and buoyant to follow the dense basaltic crust into the depths. Instead, they were scraped off like soft butter scraped from a knife and piled up at the edge of the overriding continent. Then, the inevitable finally happened. India, after its long voyage, made contact. Continental crust is too thick and buoyant to subduct easily, so when two continents meet, there is no more room for graceful descent. The collision is slow but utterly unstoppable. It is a geological marathon of compression, where the continental margins and all the scraped-off oceanic sediments trapped between them have nowhere to go but up. This monumental crumpling zone, this slow-motion train wreck of continents, is called an orogeny, the mountain-building event itself. The horizontal layers of the ancient seafloor, once laid down in tranquil sequence, are now caught in a titanic vice. They are folded into gigantic arches and troughs, fractured by immense faults, and thrust over one another in sheets miles thick. The quiet limestone becomes a towering cliff. The deep sea shale is bent into a dramatic curve. What was once the bottom of the Tethys Ocean is meticulously, violently, and beautifully uplifted to become the spine of the Himalayas. This is the ultimate answer to our detective story. Plate tectonics provides the motive, the means, and the timeline. It explains not just how the seafloor got to the top of the world, but why its structure is so complex and tortured. Every fold, every fault, every layer standing on end is a testament to that slow, irresistible collision. The mountains are not random heaps of rock. They are the direct, sculpted result of an ocean's closure and a continent's determination to keep moving. They are the lasting monument to a sea that no longer exists, forged in the furnace of planetary motion. The story of vanished oceans is not locked away in remote peaks alone. It is written into landscapes we can walk through today. The majestic Alps, with their iconic meadows and towering cliffs, offer one of the world's most accessible and complete testimonies. Here, the evidence is not hidden. It is displayed on a monumental scale in the very structure of the mountains. Geologists call them nappes, a term borrowed from the French word for tablecloth, and it is a perfect description. These are not simple layers, but colossal, recumbent folds of rock, some hundreds of meters thick and stretching for miles, that have been thrust horizontally over one another like a giant sliding a rug across a floor. Within these immense nappes, the clues we have discussed are preserved in stunning clarity. There are limestones packed with the fossils of ancient corals and shellfish, whispering of warm, shallow reefs. There are dark shales holding the delicate imprints of deep sea life. And crucially, there are ophiolites, those telltale suites of rocks that form a complete cross-section of oceanic crust, now resting high in the mountains. All of these rocks share a single birthplace, the Piedmont-Ligurian Ocean, a vanished seaway that was once a northern branch of the great Tethys Ocean. This was not a quiet inland sea, but a dynamic, deep ocean basin that separated the continents of Africa and Europe for hundreds of millions of years. Its floor accumulated the very sediments and volcanic rocks we now find in the Alps. Then, the slow but relentless dance of the plates brought Africa northward. The Piedmont-Ligurian Ocean, caught between these two continental giants, had nowhere to go. Its dense oceanic crust was forced downward and consumed, but its sedimentary blanket, the accumulated story of its existence, was too buoyant to follow. Instead, it was scraped off, folded, and stacked as the continents converged. The collision did not just push Africa into Europe, it squeezed the entire oceanic archive between them, thrusting it northward in these gigantic sheets onto the stable land of the European continent. This means a hiker crossing an alpine meadow or gazing up at a sheer cliff face is engaging with a transformed world. The ground beneath their feet, the rock of the towering peaks, is the deformed and uplifted floor of a Mesozoic sea. Every fossil, every fold in the stone, is a direct sentence in a narrative of closure and collision. The Alps are not a random collection of beautiful scenery. They are a dynamic geological document, a direct and breathtaking testament to the fact that our solid ground is the product of epic journeys and lost worlds, forever reminding us that the most permanent-looking landscapes are chapters in a story still being written. The collision that built the Himalayas is still happening today. This is the most important fact to grasp about Earth's highest mountains. They are not a relic of the distant past, but an ongoing event you can measure in real time. The Indian subcontinent continues to press northward into Asia at a rate of about 2 inches per year, a force so immense it still lifts the entire Tibetan plateau and causes the frequent, powerful earthquakes that ripple through the region. This relentless pressure means the Himalayas are, geologically speaking, still under construction. They are the youngest major mountain range on our planet, and their youth is written in their breathtaking height and their raw, jagged profiles. The story of their birth is the ultimate case study, a perfect demonstration of every clue we have explored from fossil to fold, playing out on the grandest possible stage. That story begins not with rock, but with a map of the ancient world 140 million years ago. At that time, the supercontinent of Pangaea was breaking apart, and between the separating landmasses of Africa, India, and Eurasia, a vast tropical ocean stretched across the planet. This was the Tethys Ocean, a warm, shallow sea teeming with life, its clear waters laying down the limestones that would one day become the roof of the world. For tens of millions of years, India drifted northward across this seaway, riding its tectonic plate like a colossal raft. As it moved, the oceanic crust of the Tethys ahead of it was steadily consumed, subducting beneath Eurasia. The ocean was closing, its destiny sealed. Then, around 50 million years ago, the raft reached the far shore. The continental crust of India finally made contact with Eurasia. With no more ocean floor left to easily subduct, the slow-motion collision began in earnest. The sedimentary archives of the Tethys, the limestones and shales that had accumulated over eons were caught in the middle. They were scraped off the descending plate, folded, fractured, and thrust skyward in a series of gigantic, overlapping sheets. This process created the fundamental architecture of the Himalayas, a series of parallel ranges where older rocks are often thrust over younger ones, a geological paradox that only makes sense in the context of such immense compression. The evidence is layered in the mountains themselves, a vertical timeline of this epic. At the very top, the summit pyramid of Mount Everest is a capstone of Ordovician limestone, a rock formed around 480 million years ago in a shallow, sunlit sea. Within it are the fossils of marine creatures like trilobites and crinoids, permanent residents of the peak. Beneath this limestone cap lie thousands of meters of metamorphosed sediments, rocks that were once the mud and sand of the Tethys seafloor, but have been transformed by incredible heat and pressure into tough, crystalline schists and gneisses. Deeper still, at the root of the range, are the granites, born from the melting of crustal rocks under the intense conditions of the collision. This is the complete cycle, from peaceful ocean sediment to hardened metamorphic rock to molten magma, all exposed in one breathtaking uplift. The Himalayas are therefore more than just mountains. They are a three-dimensional museum, a monument to a vanished ocean. Every trekker who passes a fossil embedded in a trailside boulder, every climber who scales a cliff of marine limestone, is interacting with the direct, uplifted legacy of the Tethys. This range demonstrates with sublime clarity that the highest places on Earth are not separate from the deepest oceans. They are their direct descendants, forged in the most powerful geological process our planet knows. While the Himalayas tell a story of continents colliding, other mountains whisper a different, equally dramatic tale of consumption. The Andes, the longest continuous mountain range on Earth, stretch like a colossal spine along the entire western edge of South America. Their formation reveals a parallel process in our planetary story, one where an ocean does not close completely, but is instead steadily devoured, feeding the growth of mountains from below. This is the relentless engine of subduction. Here, the dense oceanic crust of the Nazca Plate is not meeting another continent. It is diving directly beneath the South American continent. Imagine a colossal piece of the Pacific seafloor, thousands of miles wide, slowly but inexorably tilting downward and sliding into the Earth's hot interior. This is not a quiet process. As the plate descends, friction and increasing heat cause it to release water and other volatile elements trapped in its rocks. This material rises into the overriding wedge of continental crust above, dramatically lowering its melting point. The result is a chain of fire, the iconic volcanoes that line the Andes, and the creation of massive bodies of molten rock called batholiths that cool slowly deep underground to form granite. These fiery peaks and plutons are literally born from the melting of an oceanic plate, a direct chemical gift from the sea. But the ocean's contribution is not just molten, it is also solid and tangible. As the Nazca Plate slides downward, it does not go cleanly. Its surface is not bare rock. It is covered with a blanket of sediment, layers of mud, sand, and the skeletal remains of marine life that have accumulated over millions of years. This sedimentary veneer, too light and buoyant to follow the dense basalt into the depths, is scraped off. It piles up against the overriding continental margin in a process called accretion, like snow accumulating on a plow blade. Over immense spans of time, these scraped-off packages of deep-sea ooze and turbidite sands are compressed, hardened, and progressively lifted by the ongoing tectonic pressure. They become part of the mountain range itself, so while the Andes are famously volcanic, their foundations are often these accreted oceanic sediments, layers of fossil-rich rock that were once part of the Pacific floor, now standing thousands of meters high in the altiplano or exposed in remote canyons. This means a hiker in the Peruvian Andes might be walking on rocks that formed in abyssal plains far from any sunlight, while gazing at a volcano whose very existence is fueled by the continued consumption of that same oceanic crust. The Andes demonstrate that mountains can be built not only by the head-on crash of continents, but by the steady, grinding descent of an ocean beneath a continent, a process that meticulously stitches the history of the seafloor directly into the rising land. It is a slower, more continuous kind of construction, weaving the story of the ocean into the very fabric of the Cordillera, stone by stone, over countless epochs. The stone holds a compass, its needle frozen for hundreds of millions of years. This is the hidden power of paleomagnetism, a phenomenon that transforms ordinary-looking volcanic rock into a precise navigational logbook. When certain iron-rich minerals in lava cool and solidify, the tiny magnetic particles within them act like microscopic compass needles. They align themselves with the Earth's magnetic field at that exact moment in time, and then they lock into that position permanently. It is a snapshot of the planet's invisible magnetic field captured in stone. For geologists, this is not just a curious fact, it is a revolutionary tool. It means a piece of basalt, whether it sits on a quiet hillside or a jagged mountain ridge, carries within it a record of where on the globe it was when it first solidified. Earth's magnetic field is not uniform, it varies predictably with latitude. At the equator, magnetic field lines run parallel to the Earth's surface, while at the poles they dive steeply downward. The angle at which those fossilized magnetic particles are frozen, known as their inclination, tells a clear story. A shallow inclination points to a formation near the equator, a steep one points to formation near the poles. So, what happens when you analyze a mountain rock that was once an underwater lava flow, a piece of that ancient oceanic crust? You can ask it a direct question: where were you born? The answer can be astonishing. A chunk of pillow basalt high in the Swiss Alps might reveal a magnetic signature indicating it solidified at a latitude of 20 degrees north, squarely in the tropical realm. Today, those Alps sit at around 45 degrees north, a temperate zone. That single measurement tells us this rock, and the seafloor it was a part of, has traveled over 1,500 miles northward since its formation. It is not an estimate, it is a latitude stamp in the rock itself. This technique provides the roadmap for tectonic plates that we previously could only theorize. By sampling rocks of different ages from the same mountain belt, scientists can reconstruct the entire voyage of that slice of oceanic crust. They can trace its long journey from its fiery birth at a mid-ocean ridge, perhaps in a long-vanished ocean, across thousands of kilometers of planetary surface, to its final, crumpled resting place in a mountain chain. This paleomagnetic data confirms the vast horizontal journeys that are the prerequisite for the vertical drama we see. It turns the abstract idea of plate motion into a measurable, documented fact written in the rock's own atomic structure. The quiet stone in your hand did not just move up and down, it undertook an epic continental trek, a voyage spanning epochs before it was ever lifted towards the clouds. Its final altitude is only the last line in a much longer travelogue, written in magnetism. The rock itself remembers the violence of its journey. Deep within the mountain roots, where the tectonic collision exerts its greatest force, the original seafloor sediments do not simply bend, they are reborn. This is the realm of metamorphism, a profound transformation where the immense heat and pressure of Earth's interior act as a planetary alchemist, rewriting the very identity of the stone. It is a process so complete that a soft, flaky black shale, once the quiet mud of an ocean abyss, can emerge as a glittering schist, its surface sparkling with plates of mica that catch the light like 1,000 tiny mirrors. A bland gray limestone, the accumulated shells of ancient sea life, can recrystallize into a luminous marble, its once fossilized contents now blurred into elegant, swirling veins. These metamorphic rocks are the hardened veterans of the tectonic war, bearing the scars and medals of their ordeal in their new crystalline structure. Their value to our detective story is immense, for even when the original sedimentary features, the fossils and the pristine layers, are stretched, folded, or obliterated by the heat, the metamorphic minerals that form in their place keep a meticulous log of the conditions they endured. Each new mineral is a clue to a specific chapter of pressure and temperature. Take the stunning blue schist, a rock that gets its distinctive color from a mineral called glaucophane. This mineral is a geological whistleblower. It forms under a very peculiar set of conditions, high pressure but relatively low temperature, a combination that is the definitive fingerprint of a subduction zone. It is the signature environment where an oceanic plate is being forced down into the mantle, carrying seafloor rocks to great depths quickly enough that they do not get intensely heated, but are subjected to crushing pressure. Finding blue schist in a mountain belt is like finding a piece of a deep-sea submersible that was designed to withstand the abyss. It is direct physical proof that those rocks were once on a one-way journey into the planet's interior, only to be somehow returned to the surface. So these glittering schists and vivid marbles are far more than beautiful stone. They are a secondary archive, a pressure cooker's logbook. When the primary fossil evidence is lost in translation, the metamorphic mineralogy steps in to testify. It tells us not just that these rocks were once underwater, but precisely what kind of hellish tectonic journey they undertook to get from there to here. They record the depth of burial, the intensity of the collision, and the specific geothermal gradients of that ancient event. In this way, the mountain preserves a dual narrative, the first written by the tranquil sea, and the second, overwritten in crystalline code, by the titanic forces that lifted that sea into the sky. Even the atoms remember where they came from. Beyond the visible folds and the tangible fossils lies a deeper, more fundamental layer of evidence, written in the language of chemistry itself. Every rock is a collection of chemical elements, and within those elements are hidden variations called isotopes. Think of an element like oxygen or strontium as a family name, and the isotopes as the individual family members, each with a slightly different atomic weight. The specific mix of these isotopes in a rock forms a unique signature, a geochemical fingerprint that can survive even the most extreme heat and pressure. This is the ultimate detective tool, a way to ask the stone a direct question about its origins and get a precise, unshakable answer. Take a piece of limestone from a mountain high in the Himalayas. Chemically, it is mostly calcium carbonate, but it also contains tiny traces of other elements like strontium that were dissolved in the ancient seawater when the rock formed. The ratio of different strontium isotopes in seawater is not constant. It changes slowly and predictably over geological time as continents erode and new volcanic rocks emerge. So, when scientists measure the strontium isotope ratio in that Himalayan limestone, they can compare it to a global database, a kind of chemical timeline for Earth's oceans. They might find it matches the signature for seawater from the Ordovician period, around 480 million years ago. This is not a suggestion, it is a chemical birth certificate, placing that rock's formation in a specific window of deep time when the Tethys Ocean had a very particular chemistry. It confirms that the limestone is not just generally old, but a contemporary of the fossils it contains, both locked in the same moment of Earth's history. Similarly, the dark basalts of an ophiolite, those pieces of oceanic crust, carry their own elemental stories. Patterns of rare earth elements within them act like a barcode, tracing the magma's source deep in the mantle. One pattern might indicate magma from a mid-ocean ridge, where new crust is born, while another points to magma from a volcanic island arc. By reading this barcode, geologists can determine not just that a basalt came from the seafloor, but what specific part of the seafloor plumbing system it came from. This geochemical analysis is the forensic DNA test of geology. When all the physical features of a rock have been scrambled by metamorphism, when folds upon folds have obscured the original relationships, these isotopic signatures remain. They allow scientists to take two rock fragments from opposite ends of a mountain range, now separated by hundreds of miles of complex terrain, and prove they were once part of the same ancient oceanic plate. They can correlate a sliver of rock in Scotland with a formation in Newfoundland, reuniting pieces of a lost ocean that were scattered when the supercontinent Pangaea broke apart. These silent chemical whispers within the stone provide the final, definitive link in the chain of evidence. They transform the mountain from a beautiful but chaotic jumble into a coherent, annotated text. Each isotopic ratio is a footnote, a citation pointing back to a specific chapter in Earth's deep history, proving beyond doubt that the foundations of our highest peaks are built from the authenticated remains of vanished seas. These tectonic souvenirs are geological time capsules of breathtaking completeness. An ophiolite is not a random assortment of seafloor rocks. It is a meticulously ordered sequence, a vertical cross-section of an entire oceanic plate now lying on its side for us to examine. From the bottom up, the story unfolds. The deepest layer is peridotite, a dense, greenish rock that originates in the Earth's upper mantle, the hot, plastic layer beneath the crust. This is the foundation upon which the ocean floor was built. Above it sits gabbro, a coarse-grained crystalline rock that represents the deep magma chamber, the slow cooling heart of the oceanic crust. Then comes a dramatic transition, the sheeted dike complex. This is a stunning formation of near-vertical, parallel walls of basalt, like the pages of a colossal stone book. These dikes were the fissures, the plumbing system through which molten rock raced upward from the magma chamber to erupt onto the seafloor. And erupt it did, giving us the next most iconic layer, pillow basalts. These bulbous, rounded formations are the frozen moment of that eruption, lava instantly chilled by deep, cold seawater into these distinctive shapes. Crowning it all, like the final page of the story, are the deep-sea sediments, layers of chert and mudstone that settled like a quiet blanket over this volcanic landscape, containing the microscopic remains of organisms that lived in the water column above. To stand before a complete ophiolite, like the spectacular Seamale Ophiolite in Oman, is to walk across a petrified ocean basin. The rocks are not merely suggestive, they are definitive. The sheer scale is humbling, an entire geological environment, miles thick and hundreds of miles long, displaced from its birthplace on the ocean floor and carefully placed onto the continent. It is the equivalent of finding a fully intact shipwreck from an ancient sea, perfectly preserved on a mountain pass. This is why geologists consider an ophiolite the smoking gun, the irrefutable proof in the case of the vanished ocean. It moves the narrative from inference to direct observation. You are not just looking at rocks that formed underwater, you are traversing the actual architecture of the seafloor itself, its volcanic guts and its sedimentary skin, lifted into the dry, thin air. These formations are not just clues, they are the star witnesses, testifying under oath to the monumental forces that can move entire worlds. The wrinkled skin of the Earth tells a story of immense pressure. Across every major mountain range, from the sweeping arcs of the Appalachians to the jagged spines of the Alps, the landscape is dominated by two fundamental architectural features, folds and thrust faults. These are not random cracks or gentle undulations. They are the direct physical signature of continents in collision, the permanent wrinkles formed as the planetary crust is slowly squeezed. A fold is a majestic bend in the rock layers, like a wave frozen in stone, where once horizontal strata are warped into great arches called anticlines and corresponding troughs called synclines. A thrust fault is something even more dramatic, a fracture where one entire slab of rock, often miles thick, has been pushed up and over another, overlapping like shuffled pages in a giant book. Together, these structures form what geologists call fold and thrust belts, the very skeleton of the mountain range. To understand their significance, picture a long, elegant rug lying flat on a polished floor. Now push steadily against one end. The rug does not simply slide, it resists and begins to crumple. First, a gentle wave forms, then another, and as you keep pushing, the waves tighten and sections of the rug begin to ride up over themselves, creating overlaps. This is the essence of a fold and thrust belt, but on a scale where the rug is hundreds of miles wide and the push lasts for millions of years. The critical evidence lies in the identity of the rocks being folded and thrust. When geologists meticulously map these structures, they consistently find that the colossal sheets being crumpled and stacked are composed of the same marine sedimentary rocks we have been following, the limestones, shales, and sandstones of vanished oceans. This changes the entire interpretation. The mountains are not just piles of uplifted rock, they are the result of catastrophic shortening. Vast, horizontal expanses of ancient seafloor, once stretching across entire ocean basins, have been forcibly compressed into a narrow, vertical belt. The scale is almost incomprehensible. In the Himalayas, geological studies suggest the crust has been shortened by hundreds of miles, meaning a swath of the Earth's surface that was once as wide as the distance from New York to Chicago has been crumpled and stacked into the much narrower width of the mountain range we see today. Those marine strata are not passive passengers in this process. They often form the very core of the major thrust sheets. A single thrust sheet, a package of rock that moved as one unit, might be over a mile thick and traceable for 50 miles along the length of a mountain range, and its leading edge could be a cliff of fossil-rich limestone that was once a quiet reef. This architecture proves the seafloor did not just rise, it was actively shoved, folded, and telescoped. The quiet, orderly pages of the Oceanic archive have been violently crumpled by the closing of the book, their original sequence now contorted into a three-dimensional puzzle that geologists must carefully decode to reconstruct the lost world from which they came. This distinction is absolutely crucial for our detective story. We must separate two very different geological scenarios, one that is like a temporary flood, and another that represents a fundamental identity. The first scenario involves global sea level change, a phenomenon scientists call eustasy. There have been times in Earth's deep past, most famously during the Cretaceous period around 100 million years ago, when the planet was so warm and ice-free that sea levels were staggeringly high, perhaps over 200 meters higher than they are today. Vast inland seas, like the Western Interior Seaway that split North America in two, flooded the continents. These epic, shallow seas deposited layers of marine rock limestones and shales full of fossils directly onto what were then low-lying continental plains. If those plains were later tectonically uplifted into mountains, those marine rocks would indeed be found at high altitude, but their origin story is different. They are continental rocks that were temporarily underwater, guests in a marine environment. The second and far more profound scenario is the one we have been unraveling. Here, the rocks themselves did not just visit an ocean, they are the ocean. Their very essence, their chemical and mineralogical identity, was forged in deep oceanic settings, often far from any continent. An ophiolite is not a rock that formed on a flooded continent. It is a piece of the ocean basin's own foundation. The high-pressure, low-temperature metamorphism of blue schist does not occur in a warm, shallow inland sea. It is the exclusive signature of a subduction zone where oceanic crust is dragged into the abyss. This is the critical difference. One is a surface event, a temporary covering of water over existing land. The other is a matter of birthplace, of the rock's deepest origin in the true oceanic realm. The clues we have gathered, the pillow basalts, the deep sea cherts, the fossil assemblages of open ocean creatures, all point insistently to this second, more dramatic origin. They tell us we are not looking at mountains that were merely flooded, but at mountains that are literally built from the stitched-together remains of vanished oceans. The next time you see a fossil in a mountain rock, you can ask a more precise question. Is this a visitor from a bygone flood, or is it a native, a permanent resident of a world that has been lifted, intact, into the sky? The answer reshapes the entire narrative from a simple story of water covering land to an epic of planetary recycling, where the bones of lost seas become the skeleton of the continents themselves. The story of these vanished oceans is not confined to textbooks and mountain trails. It powers our modern world. Those dark, organic, rich shales and limestones we find folded in the mountains, the very same rocks that settled in the quiet depths of the Tethys or other ancient seas, hold a hidden legacy. They are the source, over tens of millions of years, the remains of countless microscopic algae, plankton, and other marine life settled into the mud on those oxygen-poor seafloors. Buried under ever-thickening layers of sediment, this organic soup was subjected to immense heat and pressure, a slow geological cooking process that transformed it. The result was hydrocarbons, the fundamental components of crude oil and natural gas. This means the formation of those mountains did more than just lift the seafloor. In many cases, it provided the very oven that baked this ancient life into the concentrated energy we rely on today. The tectonic drama that crumpled the rock also created perfect traps, as those marine strata were folded into great arches and thrust over one another. Impermeable layers of rock could form seals, creating natural reservoirs where the migrating oil and gas pooled. Some of the world's most significant oil and gas fields are found in precisely these geologic settings, in folded belts adjacent to ancient mountain ranges. The search for these resources is therefore a direct application of the story we have been following. Geologists looking for new energy reserves must become detectives of paleo-oceans, mapping the extent and depth of those long-vanished seas to predict where the richest organic sediments were deposited and where later tectonic forces might have trapped their transformed remains. So when we consider a mountain range, we are looking at more than a monument to a lost sea. We are looking at a vast battery. The peaks hold the concentrated solar energy captured by ancient marine ecosystems, stored as chemical energy through eons of deep time, and finally unlocked by human ingenuity. The connection is profound, linking the quiet, sun-dappled surface of a Mesozoic ocean, teeming with invisible life, to the fuel that drives a civilization. It is a reminder that the Earth's deepest histories are not abstract. They are woven into the very fabric of our present, a gift from primeval seas, delivered by the slow, relentless power of the mountains themselves. The very act of raising the seafloor into the sky triggers a cascade of planetary consequences. These newborn mountains do not stand in silent isolation. They become powerful actors in Earth's climate system, reshaping the flow of air and water across entire continents. Their immense bulk disrupts the global wind patterns, forcing moist air to rise along their windward slopes. As this air climbs, it cools and condenses, releasing torrential rains that nourish lush ecosystems on one side of the range. But every gift has its shadow. By the time the air crests the peaks and descends the leeward side, it has been wrung dry. This creates vast rain shadows, arid regions where little rain falls, transforming what might have been a continuous forest or plain into a stark desert. The contrast is dramatic. Think of the sodden, green forests of the Pacific Northwest against the dry plains east of the Cascades, or the monsoon-drenched southern Himalayas versus the high, arid Tibetan plateau to the north. This is not a minor weather effect. It is a fundamental replumbing of regional climates, all orchestrated by the presence of those towering barriers of former seafloor. The mountains become their own weather makers, and in doing so, they dictate where life can flourish and where it must struggle, drawing a stark line on the landscape with nothing but uplifted rock and the physics of the atmosphere. The climate story, however, is only half the drama. The other half is written in the relentless work of erosion. The rocks that were lifted are often the very same soft marine sediments, the limestones and shales that accumulated in peaceful seas. They are not prepared for the assault of the elements at high altitude. Once exposed to the violent realm of wind, ice, and most importantly, water, they begin to dissolve and crumble. This is where the cycle comes full circle. The tectonic forces that painstakingly lifted these sediments from the ocean are now opposed by the erosive forces determined to return them to the sea. Rivers, fed by the heavy precipitation on the windward slopes, become nature's demolition crews. They carve deep, V-shaped gorges into the soft rock, like the Kali Gandaki Gorge in Nepal, which cuts deeper than the Grand Canyon. Glaciers, slow rivers of ice, grind and scour the peaks, sculpting classic U-shaped valleys and sharp, horn-shaped summits like the Matterhorn, whose iconic form is a direct product of glacial carving on folded rock. This erosion is not merely destructive, it is profoundly creative. It is the artist that reveals the hidden architecture of the mountains. As the rivers cut down, they act like a natural drill core, exposing layer upon layer of the geological story. They unveil the gigantic folds, the thrust faults, and the intricate sequences of rock that would otherwise remain buried. The breathtaking landscapes we associate with mountains, the sheer cliffs, the deep valleys, the exposed ribs of rock, are not the product of uplift alone. They are the exquisite sculpture created by the ongoing battle between the titanic force pushing the land up and the persistent, patient power of water and ice wearing it down. Every grain of sand carried by a Himalayan river to the Bay of Bengal is a piece of the ancient Tethys Ocean beginning its long journey home, a tiny fragment in a planetary recycling program of staggering scale. The mountains stand as a temporary victory for tectonic forces, but their beautiful, rugged forms are the handwriting of erosion, a constant reminder that even the mightiest peaks are part of a grand, unending cycle that began the moment the seafloor rose. The quiet stone yields its secrets to new kinds of eyes, while the geologist's hammer and hand lens remain essential tools of the trade. Modern science has unlocked a suite of technologies that allow us to see deep into the mountain's heart and measure its slow dance with astonishing precision. One of the most powerful is seismic reflection profiling, a technique borrowed from the oil industry. It works like a geological ultrasound for the planet. Scientists create powerful vibrations at the surface, often with large trucks called vibroseis vehicles or even small explosives. The sound waves travel downward, reflecting off the boundaries between different rock layers deep within the crust. By recording the echoes with a vast array of sensitive microphones called geophones, computers can construct a detailed cross-sectional image, a slice through the earth that can reveal the geometry of ancient thrust faults and the folds of buried oceanic rock dozens of miles below the surface. This allows us to trace a single layer of limestone, a remnant of that ancient seafloor, as it dives beneath another continent, confirming the very architecture of collision. From the deep interior, we look to the sky for another critical measurement. Satellite-based interferometry, known as INSAR, uses radar signals from orbiting spacecraft to detect minuscule changes in the Earth's surface. It is so precise it can measure the ongoing uplift of a mountain range millimeter by millimeter, year by year. This data provides a real-time confirmation that the tectonic forces which began lifting the seafloor millions of years ago are still actively at work today, pushing the Himalayas a little higher with every passing season. To gather the raw material for our geochemical detective work, We go even deeper. Ambitious scientific drilling projects bore kilometers into the roots of mountain belts, retrieving long, cylindrical cores of pristine, unweathered rock. These cores are irreplaceable libraries. They preserve the exact sequence of oceanic sediments and volcanic layers in their original order, allowing for meticulous sampling. Back in the laboratory, those samples meet machines of breathtaking sensitivity. Mass spectrometers can detect the isotopic fingerprints we discussed earlier, atom by atom, in samples smaller than a grain of salt. Electron microscopes can map the microscopic textures of minerals, revealing the story of their deformation. These tools transform qualitative stories into quantitative, predictive science. They allow researchers to build intricate three-dimensional computer models of how an entire oceanic plate was subducted, scraped, and folded into a mountain range. We are no longer just reading the story in the cliffs, we are simulating the entire event, testing our hypotheses against hard data pulled from the deep earth. This technological symphony turns the grand narrative of vanished oceans from a compelling theory into a meticulously documented historical fact, written in data as enduring as the stone itself. Yet for all the evidence we have gathered, the story is far from finished. The scientific narrative of vanished oceans and rising mountains is not a closed book, but a living document filled with active debates and profound unanswered questions. Even with our sophisticated tools and deep understanding, the precise choreography of these planetary events remains a subject of intense research and spirited discussion. One of the most persistent debates centers on timing. When exactly did that ancient ocean close? When did the continents first make contact? And how quickly did the mountains begin their ascent? Different lines of evidence sometimes tell slightly different stories. Radiometric dating of volcanic ash layers trapped within the marine sediments might suggest one date for the final moments of the sea, while the magnetic signatures in the rocks or the cooling ages of minerals formed during the collision might suggest another. Piecing together a unified timeline from these disparate clocks is a constant challenge, reminding us that Earth's history is recorded in multiple, imperfect languages that we are still learning to translate perfectly. Another major puzzle lies in the mechanics of the collision itself, particularly the behavior of rock under unimaginable conditions. We know the upper crust folds and fractures in thrust sheets, but what happens deeper down, tens of kilometers below the surface? At those depths, heat and pressure are so immense that solid rock can actually flow like thick putty in a process called ductile flow. How does this deep, plastic movement influence what we see at the surface? Does it allow entire blocks of crust to move in ways our current models cannot fully predict? Understanding this deep-seated ductility is crucial, as it might explain how some of the most massive structures in mountain belts, including those colossal Ophiolite sheets, were in place. Which brings us to one of geology's most captivating mysteries. How are these immense slabs of oceanic crust, sometimes over 10 miles thick, lifted onto the continents without being completely shattered and destroyed in the process? The survival of an Ophiolite seems almost miraculous. It requires a sequence of events so precise it defies simple explanation. The oceanic slab must be detached from the descending plate but not consumed. It must then be transported scores of miles horizontally, often riding on top of younger rocks before coming to rest. Was it shoved like a bulldozer blade? Or did it slide on a layer of lubricating high-pressure minerals, or perhaps a combination of both? Each new discovery refines the model, but the complete picture remains just out of reach. These are not minor details, they are fundamental to understanding the very limits of planetary mechanics. They drive geologists to remote field sites and powerful supercomputer simulations, searching for the rules that govern how the Earth rebuilds itself. Every answered question, from the identification of a key fossil to the dating of a critical fault, inevitably leads to new, deeper mysteries. This is the beautiful, humbling essence of science. It reminds us that our planet's history is not a simple, linear tale, but a complex, sometimes counterintuitive tapestry of dynamic processes. The mountains stand not as final monuments to a solved puzzle, but as permanent invitations to keep looking, to keep questioning, and to continue unraveling the magnificent, ongoing story written in stone. This profound story does not belong only to geologists. It has become one of science's most powerful teaching tools, a natural gateway that transforms how we all see our world. Walk into any major natural history museum, and you will likely find a display centered on this very paradox, a polished slab of mountain limestone cradling a perfect fossil seashell, lit dramatically to spark that first moment of wonder. The label does not just state a fact, it poses the essential mystery that launched our entire investigation. How did this get here? That simple, tangible question is a master key. It unlocks curiosity in a way a textbook diagram of tectonic plates alone cannot. It makes the abstract shockingly concrete. A child can press their nose against the glass, see the spiral of an ancient creature, and grasp that the ground beneath us is not static, but part of a story with chapters longer than we can fathom. National parks built around mountain ranges leverage this story with powerful effect. Interpretive signs along scenic overlooks do not just name the peaks, they tell their origin story. They point to a distant cliff face and explain that its layered bands were once the muddy bottom of an inland sea, or that the colorful stones in the riverbed below are remnants of a coral reef. This transforms a beautiful view into a living diorama of deep time. A hike becomes a walk through a former ocean basin, with every switchback revealing another page of the narrative. The educational power lies in its accessibility. You do not need a degree to understand the contradiction of a seashell in the sky. That dissonance between what we expect and what we see creates a cognitive opening, a perfect place to introduce the grand ideas of plate tectonics, continental drift, and Earth's immense age. It personalizes planetary science. Suddenly, the theory is not about faraway continents moving inches per year. It is the direct explanation for the very mountain you are standing on. This engagement fosters something more valuable than rote knowledge. It cultivates a sense of planetary connection and perspective. Learning that the local hills were once a seafloor stretches the mind across hundreds of millions of years. It situates human history, with all its triumphs and challenges, within a vastly larger tapestry of natural history. Our civilizations rise and fall on landscapes that are themselves temporary features in an endless cycle of construction and erosion. This understanding can be deeply humbling and yet strangely comforting, a reminder that we are part of a dynamic, resilient system far grander than ourselves. Furthermore, following the scientific detective work, from spotting the fossil to analyzing its isotopes, demystifies the process of science itself. It shows that knowledge is not a list of facts handed down, but a painstaking, collaborative puzzle solved through observation, evidence, and relentless curiosity. The public learns to see the landscape as a collection of clues, and the scientist as a detective piecing together a cold case from the distant past. This story, therefore, does more than explain mountains. It builds a bridge between academic geology and public wonder. It turns every viewer into a potential investigator, equipped with a new lens to appreciate the slow, majestic drama of the planet they call home. The ground beneath your feet is no longer just ground. It is an archive, a monument, and an invitation to keep exploring the greatest story ever told, written in the stone of a world that is always quietly remaking itself. The same geological detective work we apply to our own planet becomes a universal toolkit. This story of vanished oceans does not end at Earth's atmosphere. It extends our vision into the cosmos, reshaping how we search for life beyond our world. Astrobiology, the study of life's potential in the universe, is deeply intertwined with geology. We cannot travel to distant stars to sample alien biology, but we can send rovers to read the rocks of our neighboring worlds. And the clues we have been following, the pillow lavas, the sedimentary layers, the chemical fingerprints, are exactly what mission scientists are trained to recognize. If the Curiosity rover on Mars were to roll over a field of bulbous, pillow-shaped basalt, the discovery would send shockwaves through the scientific community. On Earth, that texture is a definitive signature of lava meeting liquid water. On Mars, it would be powerful, though not conclusive, evidence that standing water, perhaps an ancient ocean or lake, once existed there at the same time as volcanic activity. It would move the discussion from speculation about past water to the search for specific, identifiable environments where water and energy coexisted, a fundamental recipe for life as we know it. Our understanding of Earth's full rock cycle provides the essential context for such a discovery. We know that on our planet, the presence of marine sedimentary rocks like limestone or shale is not a random event. It is the direct product of a stable, enduring aquatic environment. Finding similar layered, fine-grained rocks on another planet would be a monumental clue. It would suggest not just a momentary flood, but a persistent body of water capable of depositing sediments over long periods, a setting where life could have gained a foothold and left its own subtle traces in the stone. This transforms planetary exploration. Instead of simply looking for liquid water today, which is exceedingly rare on most planetary surfaces, we can search for the geological ghosts of ancient oceans. We look for the telltale landforms of dried-up shorelines, the mineral signatures of evaporation in vast basins, or the folded and faulted remnants of what might have been an ancient seafloor thrust up by long-dead tectonic forces. The mountains of Mars itself, like Olympus Mons, are volcanic in nature, but other regions show striking sedimentary layering that hints at a much wetter, more dynamic past. By applying the interpretive framework we built on Earth, from fossil identification to sequence stratigraphy, we can begin to reconstruct the climatic and environmental history of these distant worlds. This expands the habitable zone in both space and time. A cold, dry desert planet today might have been a warm, water-rich world 3 billion years ago, its former oceans now preserved only in the chemistry of its rocks and the structure of its oldest highlands. Our search for extraterrestrial life, therefore, becomes a form of deep-time archaeology on a planetary scale. We are not just looking for microbes in a puddle. We are learning to read the entire autobiography of a world, searching for chapters where the conditions for life were written into the landscape. The story of Earth's recycled seafloor gives us the literacy to understand those chapters, turning every alien mountain and plain into a potential page in a much larger, universal story of oceans, upheaval, and the enduring quest for living worlds. That connection to a universal search for life returns us to a fundamental truth about our own world. The most solid and permanent features in our human landscape are, in geological terms, fleeting and dynamic. To stand before a mountain, to feel its immense weight and age, and yet to know it was once the quiet floor of a sea, is to engage in a profound exercise in perspective. These ocean-covered peaks are not just geological facts, they are monuments to transience on a planetary scale. They silently testify that every form we see, every continent, every range, is a temporary arrangement in an endless cycle of creation and destruction. The sea becomes stone, the stone becomes a peak, and the peak is patiently ground back into sand, destined perhaps to one day settle on a new seafloor. This is the rhythm of deep time, a cadence measured in millions of years, far outside the pulse of our daily lives or even the entire span of human history. This perspective is both humbling and strangely liberating. It situates our brief, brilliant human story within a narrative of almost unimaginable scope. Our civilizations rise and fall on landscapes that are themselves mere paragraphs in a much longer story. The ground we build upon, the horizons that define our maps, are all chapters in a book that is still being written. This understanding fosters a particular kind of wonder, one tinged with a respectful awe for the systems that sustain our world. It can also inspire a deep sense of responsibility. If we recognize that we are momentary stewards of a planet caught in constant, beautiful flux, it reframes our relationship to it. We are not separate from these geological cycles, we are participants within them. The resources we use, the landscapes we alter, are all part of this ancient, ongoing exchange between the solid earth, the ocean, and the atmosphere. To see a mountain as a transformed seafloor is to grasp the profound interconnectivity of everything on Earth. This view does not diminish our human experience, rather, it enriches it. It connects us to a history that predates us by hundreds of millions of years and will continue long after us. It offers a quiet wisdom, reminding us that change is the only constant, and that within that grand, slow-motion dance, our role is to walk with awareness, curiosity, and care upon a world that is forever remaking itself. These geological cycles are not just a backdrop, they are the very stage upon which human history has played out. The mountains that rose from ancient seas did more than reshape the climate. They directly molded the paths of migration, the borders of empires, and the stories cultures told about their place in the world. For early human societies, a towering range like the Alps or the Himalayas was not a geological document. It was an imposing, often impassable wall. These barriers of uplifted seafloor dictated where people could travel, trade, and settle. They created natural fortresses, protecting civilizations in fertile valleys from invasion, while also isolating communities and allowing unique languages and traditions to develop in their range shadows. The mountains, born from the deep, became the definers of human geography. But our ancestors were not merely passive subjects to this terrain, they were astute observers of it. Long before the science of plate tectonics, people developed a profound practical knowledge of the mountains. They learned that certain valleys held valuable flint for tools, that specific bands of rock could be quarried for beautiful, workable marble, and that seams in the cliffs might reveal glittering metals. This was an intuitive, hands-on geology. The brilliant white marble of Carrara, sculpted by Michelangelo, is metamorphosed limestone, a rock that began as a seafloor. The tin and copper mined in ancient mountains fueled the Bronze Age, often found in veins associated with the volcanic activity of those same ancient collisions. Human innovation in its earliest forms was a dialogue with these uplifted remains of oceans. This deep connection extended into the realm of myth and spirit. Cultures around the world, from the Andes to the Mesopotamian plains, preserve stories of catastrophic floods so vast they cover the world, and of lands that rise miraculously from the waters. While these are often interpreted as memories of local floods or symbolic tales, some scholars note a fascinating resonance. Could they also be a distant, mythologized echo of a deeper truth passed down over countless generations, a folk memory of a time when the land itself was born from the sea? The very real presence of seashells on high peaks would have provided tangible, mysterious evidence to fuel such legends. For many cultures, mountains were sacred, the dwelling places of gods, seen as pillars holding up the sky or as bridges between the earthly and the divine. It is a poignant connection that the most spiritually elevated places were often physically built from the lowest, the abyssal plains. So the story written in the rock is not separate from our own. It is interwoven with the epic of human curiosity, resilience, and meaning-making. Our settlements, our art, our oldest stories, and our quest for resources are all chapters in a longer biography that began when the seafloor first stirred and reached for the sky. The final pages of this story have not yet been written. They lie in the planet's most inaccessible archives, waiting for new tools and bold questions to reveal them. The next chapters will be forged in the crushing darkness at the roots of mountain belts, and along the submerged volcanic chains that snake across the ocean floor, places where the very process of building new seafloor and consuming old crust is actively unfolding. To read these pages, science is embarking on international voyages of unprecedented scale. The International Ocean Discovery Program, a collaboration of scientists from many nations, sends advanced drilling ships to bore into the seabed, retrieving core samples that are literal timelines from the deep. These slender cylinders of mud and rock hold the unread history of ocean currents, past climates, and the very formation of oceanic crust, providing the raw data to reconstruct ancient geographies with stunning precision. Alongside these physical expeditions, another frontier is opening within the silent hum of supercomputers. Here, researchers build intricate digital simulations of tectonic collisions, modeling the behavior of rock under extreme conditions across millions of years. These are not simple animations, they are complex physics engines that test our understanding of how continents deform, how faults propagate, and how entire slabs of oceanic lithosphere are emplaced onto land. By comparing these digital models against the real-world evidence folded into mountain ranges, scientists can refine the narrative, asking what specific sequence of forces could have produced the exact structures we see today. The goals driving this work are profound. One is to move from a general story to a specific, moment-by-moment reconstruction. Researchers aim to build dynamic four-dimensional maps of vanished oceans, understanding not just their final closure, but the currents that flowed across them, the life they sustained, and the precise triggers that initiated periods of rapid, dramatic uplift. Another pressing question examines the long-term dialogue between the solid Earth and the atmosphere. How might the incremental, relentless rise of a mountain range over millions of years influence global climate patterns? And conversely, how could rapid climatic shifts, like the intense erosion from melting ice sheets, affect the very mechanics of the tectonic engine below? While these timescales dwarf human concerns, exploring them helps us see our planet as a single, deeply interconnected system, where the slow breath of geology and the quicker pulse of climate are in constant, silent conversation. The mystery of the oceans in the mountains, therefore, remains a living inquiry. Each new core sample, each refined simulation, adds a sentence, corrects a paragraph, or reveals an entirely new chapter in Earth's autobiography. From a single seashell to a landscape of stone, the evidence is overwhelming. Our world's highest peaks are not accidents of geology. They are the direct, uplifted legacy of vanished seas, a truth written in fossil and fold. This journey through deep time has revealed a planet in a state of perpetual, majestic transformation, where the solid ground is a page in a story still being written. The quiet limestone of a summit, the folded shale of a cliff face, the very architecture of a range, all whisper the same epic of closure, collision, and rebirth. Plate tectonics provides the grand narrative, but the rocks themselves are the enduring testament. They ask us to shift our perspective, to see permanence as an illusion and change as the only true constant. The next time your gaze rests on a distant mountain silhouette, whether in a photograph or from a valley floor, remember this: you are not looking at a static monument. You are witnessing a lifted seafloor, a captured piece of an ancient abyss, now standing as a monument to Earth's dynamic and restless heart. This story of oceans in the sky is one of our planet's most profound secrets, a reminder that the ground beneath us holds chapters far older and more dramatic than we often allow ourselves to see. If this exploration of planetary mysteries has captivated you, there are countless more stories written in stone waiting to be unraveled. Consider subscribing to join us for more deep dives into Earth's hidden past. And we would love to hear from you. What questions do these oceanic clues bring to your mind? Share your thoughts and reflections in the comments below.